Am I audible? Please ask your friends to join the class. Okay. Ask everyone to join the class. Okay, I'm sharing my screen. Okay, let me know if it is visible or not. Today we'll see a problem. We'll see the column chapter. Okay, stability of column. So we'll solve some numericals on Euler's formula. Okay, hope you all remember what is Euler's formula. P is equal to pi square EI by L square, right? Okay, screen is visible. Screen is visible. Okay. Okay, so we'll see a problem with we know for Euler's problem we have different end conditions, right? Both end fixed, both end hinged, one end fixed and one end is free, one end fixed and one end is hinged, right? So for the four conditions we'll solve one by one. We'll see one example. Okay, so first go through the video, then I'll explain each every step. Okay, let me know if the volume is okay or not.
Problem for column buckling. We basically just want to figure out what is the critical load. Alright, welcome back guys. In this video we are doing an example problem for column buckling. We basically just want to figure out what is the critical load and then what is our allowable load based on our factor of safety here. We want to check it against buckling. In this case this column can buckle in two directions. We have to check both of those. Then we also want to make sure that it's not going to hit the material.
So it is a both end hinge beam of length 3 meter, I guess, yes, and it has a dimension. It is given A to 20 mm, B is 40 mm, and the properties are given. Elastic Young's modulus as 200 GPa. Yield stress is given 250 MPa and factor of safety is given 2.5a. First we'll find out the crippling load of the crippling load or Euler's load, for that means the capital P for this condition beam, okay, where the beam is both hinged. This is the practical example it has shown. Okay, so let's see the solution.
Won't yield before it buckles. So looking at this, we have a three-dimensional column here. And we're talking about this as pinned joints, a pin on each end. So we'll basically treat these as ball and socket joints. So they're able to, basically this pin, it's like a pin in 360 degrees. But because this rectangular cross-section has kind of two distinct ways it can buckle basically in the YZ plane. So sort of as we're looking, it's left, it can buckle from left to right or right to left, like that way. Or it can also buckle in the XZ plane. So basically going kind of into the page that way or kind of out of the page that way. So
Okay, let me share once again. Okay, let me share once again. Oh, I thought. Okay, let me share once again. First, let's see with column buckling. Okay, let's start with column buckling.
Which column is
Now,
most
is it
likely
visible?
to buckle? A pin connection on both ends, and this little signal here means it's a pin connection. So you can picture it like a rod being held between your
Screen is
fingers.
visible?
That's a pin connection. You can kind of pivot. A moment connection on one end and free or no connection on the top. A moment connection on both ends, and a moment connection
Okay.
would be more like a rod being
So
held
let's
in your
just
fist.
go through this video, then we'll solve the numerical.
Go ahead and hit pause.
So these are the different types of beam end conditions for a
The
column.
answer is this one, the moment connection on one end and free no connection on the other. So this is a little bit counterintuitive, but there are different ways to brace a column. And we have pin connections, we have moment connections, we have free connections, which are a little bit more unusual, and we have ones that are allowed to translate right to left, and we'll get to those. So if a column is going to buckle, we need to figure out not only the strength of the column and the length of the column, but the type of connection at the top and the bottom is going to kind of govern its likelihood of buckling. Now we're looking at a table, and here you have just different flavors of column. So in A, you have fixed up, top, and bottom. On B, you have a pin connection at the top and fixed at the bottom. On C, you have something that's a rotation fixed but translation free on the top, and something that's rotation and translation fixed on the bottom. On D, we have two pin connections. On E, you have something that's fixed on the bottom and allowed to kind of move around at the top. And then on F, we have something that has a pin connection on the bottom and translation on the top. Now, what we're going to need to do when we do the calculation, when we kind of figure out likelihood of buckling, we're going to have to run through a formula, and I'm not going to get into the formula right here, but in that formula, there's a value of what's called K. And that K value, you'd look up on this table to determine its likelihood of buckling. And a higher K value means a higher likelihood of buckling, because in the formula, you're going to take the length of the column and you're going to multiply it by K. So in this one right here, we're going to take the length of the column and we're going to multiply it by 1/2. We're going to multiply it by 0.5. That means from a buckling point of view, this column of, say, 10 feet will behave more like a column that's only 5 feet. If we look at this one here, if we have a column that's fixed on the bottom and it has a pin connection on the top and it's 10 feet long, in terms of its likelihood of buckling, we're going to multiply it by 0.7, so a 10-foot column will look more like a 7-foot column when we size it for buckling. And then this is kind of our baseline. We have pin connections at the top and the bottom, which means that it's rotation free and translation fixed. And that's our 1. So then if we have a 10-foot column, it's going to really behave like a 10-foot column. But look at these two here. These two have a theoretical K-value of 2, which means that we're going to have to take a 10-foot column if we have one of these, and it's going to behave like a 20-foot column. So we're going to multiply it by 2. Now, right below that theoretical K-value, there's another line that says recommended design value when ideal conditions are approximated. And that basically means we're talking about wood. So the theoretical K-value can pretty much work if we're talking about something like steel that's pretty consistent, maybe even concrete that's pretty consistent, but wood is kind of weird. It's got knots and it's got wanes and checks and cups, and no piece of wood is perfect. No two are the same. So in this case, we're actually, in some of these situations, we're going to have a slightly larger recommended K-value for wood. So let's go through examples of what we mean by rotation fixed and translation fixed and so forth. So this is a moment connection. We saw this before when we talked about steel. It's a moment connection because we've engaged the flange and the web, and we're holding both of them in place. And so that would be a rotation fixed and translation fixed. It's not going to slide up and down. It's not going to rotate. This is what we called a shear connection before. This one is what we would, in the language of that chart we just looked at, that table we just looked at, we would call this rotation free and translation fixed. It's not able to slide up and down, but even though there are 3 bolts there, it is actually able to kind of pivot because at the scale of the building, those 3 bolts are really kind of like a pin. Then we have rotation fixed and translation free. Go ahead and hit pause and try to determine where we use that kind of connection. It's in seismic. So remember we talked about buildings kind of sliding back and forth. And you'll note that we talked about structures in all kinds of other places, right? We talked about it certainly in steel, but in other places as well. So these are the seismic isolations that are in this case, under the Utah State Capitol. If we want something to be able to slide back and forth, that's going to be something we're going to call rotation fixed and translation free. So it can't pivot, but it can translate right to left. Finally, we have our rotation free and translation free. And certainly, of course, a flagpole comes to mind. What kind of works with this at this level? It's kind of rare, and it's not very common in buildings. We sometimes will see it if we have like a single column for a highway overpass. That may behave like something that is rotation free and translation free. Now, I just gave a in-person seminar at AIA New York, and one of the participants in that seminar asked, what about a really tall, slender building? Would that kind of behave at the scale of the building? If you were worried about buckling for the building, would that kind of behave in this way like a flagpole? And the answer is kind of yes, but in practice, the buckling would not be the biggest issue. In other words, you'd be much more concerned about other things. So the buckling for a tall building, first of all, buildings aren't quite that tall and slender like a flagpole. And secondly, there would be other factors for the building that would require beefier structure, and it would be unlikely that buckling would control. But yes, same principle.
Alright, welcome back guys. In this video we are doing an example problem for column buckling. We basically just want to figure out what is the critical load and then what is our allowable load based on our factor of safety here. We want to check it against buckling. In this case this column can buckle in two directions. We have to check both of those. Then we also want to make sure that it's not going to yield, the material won't yield before it buckles. So looking at this, we have a three-dimensional column here. And we're talking about this as pinned joints, a pin on each end. So we'll basically treat these as ball and socket joints. So they're able to, basically this pin, it's like a pin in 360 degrees. But because this rectangular cross section has kind of two distinct ways it can buckle basically in the YZ plane. So sort of as we're looking, it's left, it can buckle from left to right or right to left, like that way. Or it can also buckle in the XZ plane, so basically going kind of into the page that way or kind of out of the page that way. So basically what we need to do is we need to first figure out what our effective length is. Now in both, considering both planes it can buckle in, it's considered to be pinned in both of those directions, so our effective length, no matter how we look at it, is going to be just the actual length of the column because it's that pin connection. Now that came from the previous videos where we're talking about different end connections, but in the next videos we'll do different examples. So for now, effective length is equal to the length where we have pin-pin connection on this column. Alright, the next thing that we need to do is we are going to be using this expression here that is, we're going to be looking for the P-crit, the critical load that's going to basically be where the column is going to have the tendency to buckle, so that is equal to, that is pi squared EI over LE squared. So we need to figure out what the moment of inertia is, and because we have this rectangular cross section, we're gonna have to figure out two different moments of inertia depending on which way we're thinking about this column buckling. So for the moment, we're gonna use we can calculate. Let's calculate it up here. So for let's do it down here. I'm really indecisive right now. So for Iy, basically the moment of inertia about the y-axis here, this is going to be equal to 1/12 times b times a cubed, right? Because when we're looking at this about the y-axis, this a, if we normally think about this as 1/12 base height cubed, this a kind of becomes our height. So we can plug in the values and we get 0.0267 times 10 to the negative 6 meters 4. And then we can also find the moment of inertia about the x-axis, which is what we're going to be using for buckling in the xz plane. And we find that to be equal to 0.1067 times 10 to the negative 6 meters 4. So now we have everything we need to find the critical load in buckling in each plane, basically in the YZ plane and the XZ plane. So let's go and plug those in. So we have P crit. Let's consider buckling in the YZ plane first, and again YZ basically could buckle that way or it could buckle that way. So we just need to sub in that we have pi squared E, and in this case we're using Iy, right, the moment of inertia about the y-axis, and then this is over LE squared. So if we just plug that in, we're going to find that in the YZ plane that P crit is equal to 5.9 kilonewtons. Then when we check for P critical in the XZ plane, we're going to have to basically just redo this expression. So we have P crit in the XZ plane, and that's just going to be equal to pi squared EI, and this is with the subscript x because we're looking at the moment of inertia about the x-axis now, and this is over LE squared. So we're just going to find that that is equal to 23.4 kilonewtons. And now what we want to do is we just compare the two different critical loads. So we have, for buckling in the YZ plane, the critical load is 5.9 kilonewtons, and for buckling in the XZ plane, our critical load is 23.4 kilonewtons. And intuitively this makes sense. The skinny, basically we're saying that we need a smaller load here to make a buckle in the direction that has basically a smaller amount of material basically around that axis. So if we applied, let's say 6 kilonewtons, then we will have crossed this threshold and we're most likely going to be getting buckling. So 5.9 kilonewtons is the value that we have to take for P critical for the whole column. Now, if we want to use that, we can figure out our allowable load if we set our factor of safety up here as 2.5. So basically, we can just say that the if you remember, the factor of safety is equal to the ultimate load over the allowable load. And if our ultimate load for buckling is 5.9 kilonewtons, then all we have to do for allowable load is that's going to be equal to 5.9 kilonewtons over 2.5. I'll write that a little bit cleaner, 2.5. So our allowable load for buckling with this factor of safety of 2.5 is going to be 2.36 kilonewtons. So that's something to watch out with these problems, is typically you're always going to have to check for buckling in two directions and then take the smaller value, and then if you're talking about factor of safety, like maybe your professor's only asking for you to calculate P crit, but if you're looking for the actual allowable load, then take that factor of safety into consideration. The one other thing that we can check with a column problem is it's possible that the column buckles before it yields, or it's also possible that the column yields before it buckles. So if we want to just quickly check that this column won't yield before it buckles and that this is in fact our true allowable load, then what we just need to do is if we come back up to the top here, the yield stress was 250 megapascals for this particular material. So if we know that, let's just write this in. So we have yield stress is equal to 250 MPa. Now, we know that stress is equal to force over area, right? So this is equal to the applied load over the area. Now, our cross-sectional area is going to be, if we do that up here, we have area is going to be equal to base times height, basically the cross-sectional area. So 20 millimeters times 40 millimeters, that is 800 millimeters squared. So we'll bring that down, and we'll be basically just calculating for our yield load here, the load that will cause yielding. So just multiply area to that yield stress, and we're going to get this expression here where we have that yielding load is going, or the ultimate load basically, is going to be equal to 250 MPa times, and you know what, I like to write out the units like this, so 250 times 10 to the 6 newtons per meter squared times that area, which was 800 millimeters. That's also just 800 times 10 to the minus 6 meters squared, so those meters are going to cancel out. And the value that we're going to get is just 200,000 newtons. 200,000 newtons, which is equal to basically 200 kilonewtons. Alright, so if we take, this is our yield, this is our ultimate load. If we just check again using the same thing, factor of safety is equal to allowable over ultimate, then that means that our allowable load for yielding is going to be equal to just 200 kilonewtons divided by 2.5, and that is going to give us a value of 80 kilonewtons. So we're definitely going to buckle before that. If we apply 5.9 kilonewtons, then we're most likely going to buckle. And that's that's important to look at, because if you look at this column, it is quite long, right? It is 3 meters long, and it's very slender. So it's a very slender column, and very slender columns are very prone to buckling. So in this case, it will definitely it will buckle in the YZ plane before it buckles in the XZ plane and before it yields.
Hope problem is clear. Any issues? So what they have done, this is the column is given with both and hinge. Okay. Then they found out the critical. See, this is a rectangle section, so moment of inertia. Your I will be Your I will be in two direction. One is X and Y. Okay. So first we'll find out the moment of inertia of the both. And this is the formula we know, general formula P is equal to pi square EI by LE square. So we need I to solve this. Okay. Before that, as this is a both end hinge, so your effective length LE will be same L. Okay. So pi square EI by LE square. Pi square EI by LE square. Okay. So this is the, in this formula we have I value. So they have found out IY and IX for this rectangle section. Okay. Now from for both the values you need to find the critical value along X and along Y direction. So they have found out X and Y. Now you have to take the lowest values of the both. You have to take the lowest value for your critical load, because at the, you have to take the lowest load. That means at this load it will buckle. Okay. After finding out the Px and Py, along the Px and Py, you need to find which one is least, and that you have to take. Okay. This is Py, along the Py is 5.9, along the X it is 23.4. So you have to take this load 5.9. Okay. Then factor of safety is given. You can find out the allowable load. How much will be the allowable load in this column? With this condition, you can find by this formula. Fs is equal to ultimate by allowable. So ultimate is 5.9 and divided by 2 factor of safety will get the allowable load. So my allowable load is 2.36 kilonewton. Okay. Then
That this column won't yield because 200 yield stress is equal to
then I can check that this allowable load of this column will buckle first by buckling or yielding. Okay. So I can check because there is a yield stress is given. I can find out the yield force also. Py by A. So multiply that yield stress, the sigma y, with the area, you'll get P at yielding point. So which is 2 kilonewton. So that means our column will buckle. This value is more than this buckling load. Okay. So my column will buckle because of my column will buckle first before yielding. Okay.
if we take this is our yield over ultimate
So that's how.
200 kilonewton, we're
See.
definitely going to buckle.
So yielding allowable load is 80 kilonewton, which is more than your buckling load. So the my column will fail due to buckling first. Okay. So I have to give resistance. I have to take measures for minimizing this buckling load. So that's about this problem. Please write your roll numbers in the chat box. Hope everyone wrote their roll number. Okay, join for the next class after 10-15 minutes. Okay.